Hello there, and welcome back to the Science Sleepy Minds, that cozy little corner of the internet where we explore the universe's most fascinating mysteries while you drift off into dreamland. Tonight, you find yourself standing at the edge of everything humanity has ever known about speed, distance, and the cruel cosmic joke that keeps us trapped in our tiny corner of the Milky Way. Picture this: you're gazing up at the night sky, those distant pinpricks of light twinkling like nature's own fairy lights, and somewhere in the back of your mind a thought forms. Those stars are so impossibly far away that even light itself, the fastest thing in the known universe, takes years, decades, centuries, sometimes millennia to make the journey. And here you are, a fragile bag of mostly water, wondering if humanity will ever find a way to cross those impossible distances. Spoiler alert: if you tried to reach even the nearest star using today's technology, you probably won't survive this journey. Actually, your great-great-great-grandchildren probably won't either. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And hey, drop a comment telling me where you're listening from and what time it is there. I always love knowing that someone in Tokyo is drifting off at midnight while someone in London is catching this during a lazy afternoon. We're all connected by these strange cosmic stories, scattered across time zones like stars across the galaxy. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You've grown up accepting certain truths as absolute. The sky is blue, water is wet, nothing travels faster than light. That last one feels particularly cruel when you really think about it. The universe stretches out in every direction for billions of light years, filled with wonders we can barely imagine. Alien worlds with purple skies and methane oceans, galaxies colliding in slow-motion cosmic ballets, perhaps even civilizations looking back at us wondering the same things we wonder about them. And yet, physics itself seems to have built an unbreakable wall around our little planetary neighborhood, whispering that we can look, but never touch. Light travels at approximately 299,792 kilometers per second. That sounds impossibly fast until you realize that even at that breakneck pace, light from the Sun takes about 8 minutes to reach Earth. Light from Proxima Centauri, our nearest stellar neighbour, takes over 4 years. Light from the Andromeda Galaxy has been travelling for 2.5 million years before it finally lands on your retina. The universe operates on timescales that make human lifespans look like the blink of a cosmic eye. Here's a mainstream historical fact that shaped everything we understand about this speed limit. In 1905, a young patent clerk named Albert Einstein published a paper that would fundamentally transform physics. His theory of special relativity established that the speed of light isn't just very fast, it's a fundamental constant of the universe, woven into the very fabric of space-time itself. This wasn't just Einstein being clever. Experiments had been pointing toward this conclusion for decades. The famous Michelson-Morley experiment of 1887 had already demonstrated that light speed remained constant regardless of how the observer moved, which baffled scientists who expected it to behave like every other type of wave. Now here's a quirky little tidbit that most people don't know. Einstein didn't actually win his Nobel Prize for relativity. The Nobel Committee found his ideas too controversial, and instead awarded him the prize for explaining the photoelectric effect. Imagine revolutionizing humanity's understanding of space and time, and the official recognition comes for something entirely different. Science can be wonderfully absurd sometimes. Historians still argue whether Einstein's breakthrough was inevitable, whether someone else would have pieced together relativity within a few years anyway, or whether his particular genius was truly irreplaceable. Some point to the work of Hendrik Lorentz and Henri Poincaré, who were circling similar ideas around the same time. Others insist that Einstein's conceptual leap was so profound that it might have taken decades longer without him. Either way, his equations locked humanity into a universe with a cosmic speed limit that seemed absolutely unbreakable. You shift in your bed, pulling the covers a little closer, and you think about what this really means. If you wanted to travel to another star system within a human lifetime, you'd need to somehow cheat the laws of physics themselves. Conventional rockets won't cut it. Even our fastest spacecraft, travelling at tens of thousands of kilometers per hour, would take tens of thousands of years to reach the nearest stars. Ion drives, solar sails, even theoretical nuclear pulse propulsion systems all fall catastrophically short. The distances involved aren't just large, they're actively hostile to biological life and human patience. But here's the beautiful thing about science. Physicists rarely accept impossible as a final answer. They treat it more like a challenge, a puzzle to be solved, a lock waiting for the right key. And over the past few decades, a small but dedicated community of researchers has been quietly working on something extraordinary. They've been asking a deceptively simple question. What if there's a loophole? What if you could travel faster than light without actually breaking the speed limit? It sounds like semantic trickery, and honestly it kind of is. But it's semantic trickery grounded in the most rigorous mathematics humanity has ever developed. The key insight comes from understanding exactly what Einstein's equations actually prohibit. They don't say nothing can travel faster than light in some absolute sense. They say nothing can travel faster than light through space. But what if space itself could move? What if you could somehow surf on a wave of warped space-time, carried along like a surfer riding an ocean swell, technically stationary relative to the water beneath your board, while the wave itself carries you forward at tremendous speed? This is the foundation of what scientists call warp drive theory, and it's not just science fiction anymore. Well, it's still mostly science fiction, but it's increasingly science fiction with serious mathematical backing. And very recently, researchers have proposed something genuinely new, a way to potentially create these space-time distortions without requiring the exotic, impossible materials that previous theories demanded. You feel your eyelids growing heavier as you contemplate these ideas. Somewhere out there, beyond the warm cocoon of your blankets, physicists are scribbling equations on whiteboards, running computer simulations, and daring to imagine a future where the stars might finally be within reach. Tonight, you're going to join them on that journey, drifting through the mathematics of bent space and impossible dreams, letting the soft hum of theoretical physics carry you off to sleep. The universe may have set a speed limit, but humanity has never been particularly good at following rules. You settle deeper into your pillow, and your thoughts drift back to that young patent clerk in Switzerland, scratching equations onto paper that would reshape everything. Albert Einstein wasn't trying to build starships when he developed special relativity. He was trying to solve a puzzle that had been nagging at physicists for decades. Why did light behave so strangely? Why did its speed remain constant no matter how you measured it? The answer he found was elegant, revolutionary, and utterly devastating for anyone who dreamed of racing between the stars. Special relativity rests on two deceptively simple principles. First, the laws of physics work the same way for everyone moving at constant speed. There's no special, stationary frame of reference in the universe. Second, the speed of light in a vacuum is always the same, regardless of how fast you're moving toward or away from the light source. These two ideas, combined with careful mathematical reasoning, produce conclusions that feel almost offensive to common sense. Imagine you're floating in space, watching a beam of light pass by. You measure its speed, 299,792 kilometers per second. Now imagine you start chasing that light beam at half the speed of light itself. Intuition says the light should now appear to be moving at half its original speed relative to you, just like a car pulling away from you seems slower when you're driving in the same direction. But that's not what happens. You measure the light again, and it's still travelling at exactly 299,792 kilometres per second relative to you. It hasn't slowed down at all. This bizarre behaviour only makes sense if space and time themselves are flexible. Einstein realised that as you move faster, time itself slows down for you, relative to someone standing still. Distances also contract in your direction of motion. These effects are imperceptible at everyday speeds. You don't notice time dilation when you drive to the grocery store, but they become dramatic as you approach light speed. At 90% the speed of light, time for you passes at less than half the rate it passes for stationary observers. At 99% the effect is even more extreme, and at light speed itself, time would stop entirely. Here's a mainstream historical fact that demonstrates just how real these effects are. In 1971, physicists Joseph Heffel and Richard Keating flew atomic clocks around the world on commercial aircraft and compared them to clocks that stayed on the ground. The flying clocks showed slightly different times, exactly matching Einstein's predictions. Time dilation isn't a thought experiment, it's measurable reality, and GPS satellites have to account for it every single day to maintain their accuracy. But here's the truly crushing part for would-be interstellar travellers. As an object with mass accelerates toward the speed of light, something troubling happens to its inertia. It takes more and more energy to accelerate it further. The closer you get to light speed, the more your effective mass increases from the perspective of anyone trying to push you faster. At light speed, your effective mass would become infinite, requiring infinite energy to maintain. This isn't a technical problem that better engineering can solve, it's built into the structure of the universe itself. You yawn softly, imagining a rocket trying to break this barrier. Picture the engines roaring, fuel burning at unimaginable rates, the spacecraft accelerating faster and faster. At first, progress feels good. You reach 10% of light speed, then 20%, then 50%. But as you push harder, you notice something wrong. The same amount of fuel that once gave you substantial acceleration now barely nudges the speedometer. You're burning through resources at an exponential rate for diminishing returns. No matter how powerful your engines, no matter how much fuel you carry, you asymptotically approach light speed, but never quite reach it. The universe has built a wall, and that wall has no door. Now here's a quirky tidbit that adds a touch of irony to Einstein's legacy. The man who discovered that the speed of light is nature's ultimate speed limit actually hated some of the implications of his own theories. Einstein spent much of his later life uncomfortable with quantum mechanics, famously declaring that God doesn't play dice with the universe. He sought unified theories that would restore determinism to physics. The cosmos, it seems, didn't particularly care what Einstein preferred. Historians still argue whether Einstein fully appreciated the cosmological implications of his work during his lifetime. Some scholars suggest he was more focused on the elegant mathematical structure than on what it meant for humanity's future among the stars. Others point to his correspondence and note a deep melancholy about certain aspects of what his equations revealed. Either way, the beautiful prison he discovered has confined our dreams ever since. You think about what this means practically. Every science fiction story featuring starships zooming between solar systems is essentially fantasy, at least by conventional physics. Those dramatic hyperspace jumps, those sleek vessels accelerating to impossible velocities, they're all violating rules that seem absolutely foundational to how the universe operates. It's like writing a story where characters routinely walk through solid walls or travel backward in time. Fun to imagine, but not how reality works. And yet, there's a word in that previous paragraph that deserves scrutiny: conventional. Einstein's special relativity describes physics in flat, uncurved space-time. the kind of space-time you get far from any massive objects, where gravity is negligible. But Einstein didn't stop there. A decade after special relativity, he unveiled something even more profound: general relativity. And general relativity reveals that space-time isn't just a passive stage where physics happens. It's a dynamic participant, capable of bending, stretching, and warping in response to mass and energy. In general relativity, gravity isn't a force in the traditional sense. It's the curvature of space-time itself. The Earth doesn't pull you toward it through some invisible tether. Instead, the Earth's mass bends the space-time around it, and you naturally follow the curved path. This might sound like semantics, but the distinction matters enormously. Because if space-time can curve, if it can be shaped and distorted by the presence of energy and matter, then perhaps there are configurations of space-time that could allow something very much like faster-than-light travel without technically violating the light-speed barrier. You feel a small spark of hope kindling in your drowsy mind. Maybe the cosmic prison has a secret passage after all. Maybe the rules aren't quite as absolute as they first appeared. The mathematics of curved space-time contain possibilities that Einstein himself never fully explored. Possibilities that would wait decades before another physicist picked up the thread. The stars outside your window seem to twinkle with renewed possibility as you drift closer to sleep, knowing that the story has only just begun. The year is 1994, and you imagine yourself as a young physicist named Miguel Alcubierre, sitting in a modest office somewhere in Wales, probably drinking tea that's gone cold because you've been scribbling equations for hours. You've been thinking about Star Trek. Yes, really, Star Trek. The warp drive that propels the Enterprise through the galaxy has always struck you as scientifically interesting, even if everyone assumes it's pure fantasy. But what if the fantasy could be grounded in real physics? What if there's a mathematical framework that could describe something similar? This is how science often progresses, you realise as you nestle deeper into your blankets. It's not always serious people in lab coats pursuing serious research agendas. Sometimes it's a curious mind wondering if a science fiction concept might have a kernel of truth hidden beneath the technobabble. And Alcubierre, trained in the rigorous mathematics of general relativity, had the tools to actually investigate. General relativity is described by Einstein's field equations, a set of 10 interconnected differential equations that relate the curvature of spacetime to the distribution of matter and energy within it. These equations are notoriously difficult to solve. Most exact solutions describe highly idealized situations like perfectly spherical stars or completely empty universes. But the equations are also incredibly permissive. They allow for all sorts of strange space-time geometries, many of which have never been observed in nature but aren't explicitly forbidden by the mathematics. Alcubierre asked a deceptively simple question. Is there any space-time geometry that would allow a region of space to effectively travel faster than light relative to distant observers? Not a physical object accelerating through space. Einstein had firmly closed that door, but a region of space itself, a bubble of normal space-time riding on a wave of distortion. Here's a mainstream historical fact that informed Alcubierre's thinking. The expansion of the universe itself demonstrates that space can move faster than light. Galaxies at the edge of the observable universe are receding from us faster than light due to the expansion of space itself. Yet this doesn't violate relativity because nothing is actually moving through space at superluminal speeds. The space between us and those distant galaxies is simply stretching. If space can expand faster than light on cosmic scales, perhaps it could be manipulated to do something similar on smaller, more useful scales. Alcubierre's breakthrough came when he worked backward from what he wanted to achieve. Instead of starting with a physical setup and calculating the resulting space-time geometry, he started with the desired geometry and calculated what distribution of matter and energy would be needed to produce it. The geometry he wanted was elegant. a bubble of flat, normal space-time surrounded by a shell of distortion. In front of the bubble, space would contract. Behind it, space would expand. The bubble would surf on this wave of space-time carried forward while everything inside remained stationary, relative to the bubble's interior. You might imagine it like this. Picture yourself standing on a moving walkway at an airport. You're not walking at all, you're just standing still on the walkway. But relative to people standing on the regular floor, you're moving quite fast. Now imagine the walkway could move faster than any human could run, faster even than any vehicle could drive. You'd still be stationary on the walkway, but you'd be covering ground at incredible speed. Alcubierre's warp bubble works on the same principle, except the walkway is made of warped space-time rather than rubber and metal. Here's a quirky tidbit about the origin of this idea. Alcubierre explicitly credited Star Trek in his original paper. This was somewhat unusual for academic physics. Most researchers prefer to cite other peer-reviewed papers and established theoretical frameworks rather than television shows. But Alcubierre was refreshingly honest about his inspiration, noting that the warp drive concept from the show had motivated his investigation. Science fiction and science fact have always enjoyed a complicated, productive relationship. Historians still argue whether Alcubierre's paper would have received the attention it did without the Star Trek connection. Some suggest the catchy warp drive terminology helped the idea penetrate popular culture and attract funding and interest that more dryly named proposals might have missed. Others argue that the mathematics was strong enough to stand on its own merits regardless of branding. Either way, the paper sparked a small but dedicated research community that continues working on these ideas today. The mathematics of the Alcubierre drive are genuinely beautiful. The metric, the mathematical object that describes the geometry of space-time, describes a bubble where an occupant would experience no acceleration, no time dilation relative to the destination, and no apparent violation of local physics. Inside the bubble, you could float comfortably, sip coffee, read a book, completely unaware that space itself is warping dramatically just outside your window. The journey from one star to another could take days or weeks from your perspective, matching the same duration experienced by observers at your destination. This last point is crucial and often misunderstood. In conventional near-light speed travel, time dilation creates devastating consequences. You might travel to a star 40 light-years away, in what feels like a few years of ship time, but when you arrive, 40-plus years will have passed on Earth. Everyone you knew will have aged or died. Returning home means returning to a world you no longer recognize. It's the loneliest kind of travel imaginable. But in a warp bubble, time flows normally both inside and outside. You could visit distant stars and return to find your friends and family just as you left them. You smile softly in the darkness, imagining a future where such journeys might be possible, where humanity could genuinely become a spacefaring civilization, spreading across the galaxy without sacrificing generations to the void, where the stars might become neighbours rather than distant, untouchable lights. But your smile fades slightly as you remember that beautiful theories often crash against harsh realities. And Alcubierre's warp drive, for all its mathematical elegance, came with a devastating price tag that made it essentially impossible to build. The dream, it seemed, was still trapped behind a wall, just a different wall than before. You're still thinking about that beautiful bubble of warped space-time when reality comes knocking with a particularly heavy fist. Because here's the thing about Alcubierre's warp drive. When he calculated what kind of matter and energy would be needed to actually create that space-time geometry, the answer was deeply discouraging. The mathematics demanded something that might not even exist in our universe, and even if it did exist, the quantities required were absolutely absurd. The culprit is something called exotic matter, and before you drift off entirely, you should understand why this concept haunted physicists for decades. In everyday experience, all matter has positive energy density. The sandwich you ate for dinner, the blanket keeping you warm, the air filling your lungs, all of it contributes positive energy to the universe. Exotic matter, by contrast, would have negative energy density. It would gravitationally repel normal matter rather than attract it. And while this might sound like it violates some fundamental law, general relativity doesn't explicitly forbid such stuff from existing. The Alcubierre metric requires a shell of this exotic matter surrounding the warp bubble. The exotic matter is what creates the asymmetric space-time distortion, the contraction in front and expansion behind, that makes the bubble move. Without exotic matter, the whole construction falls apart. It would be like trying to build a house without any materials, just a beautiful architectural blueprint that can never become real. Here's a mainstream historical fact that puts the energy requirements in perspective. When physicists first calculated how much exotic matter the Alcubierre drive would need, the numbers were staggering. Early estimates suggested you would need negative energy, equivalent to the total mass energy of Jupiter, the largest planet in our solar system, just to create a bubble large enough for a small spacecraft. Later calculations found ways to reduce this requirement somewhat, but even optimistic estimates still demanded negative energy, equivalent to millions of tons. For comparison, the largest nuclear weapons ever detonated released energy equivalent to about 50 megatons of TNT. We're talking about requirements that dwarf anything humanity has ever produced by factors of trillions. And that's assuming exotic matter can be created at all. Here's where the physics gets genuinely murky. In classical general relativity, there's nothing preventing exotic matter from existing. The equations work perfectly fine with negative energy densities. But classical general relativity isn't the whole story. At very small scales, quantum mechanics takes over, and quantum mechanics has strong opinions about what kinds of energy states are allowed. Most physicists believe that stable, macroscopic quantities of exotic matter are probably forbidden by quantum mechanics. There are theorems, with delightfully technical names like the averaged weak energy condition, that seem to prohibit the kind of sustained negative energy densities Alcubierre's drive requires. These aren't absolute proofs, and there are potential loopholes that researchers continue to explore, but the mainstream consensus is skeptical. Now here's a quirky tidbit that keeps hope alive despite all this pessimism. Quantum mechanics does allow tiny amounts of negative energy density under specific circumstances. The phenomenon is fleeting and microscopic, but it's real. We'll talk more about this later, but for now, just know that exotic matter isn't entirely relegated to the realm of fantasy. It's more like a mythical creature that occasionally leaves footprints, tantalizing hints that it might exist somewhere, even if we've never clearly seen it. Historians still argue whether Alcubierre knew from the beginning that his drive would face these energy problems, or whether he hoped the numbers might work out more favourably. Some scholars suggest he viewed the paper primarily as a proof of concept, demonstrating that superluminal travel wasn't fundamentally forbidden by physics, even if the practical requirements were daunting. Others believe he genuinely hoped that further research might find ways to reduce the exotic matter requirements to something manageable. You yawn deeply, feeling the weight of these impossible numbers pressing down on your eyelids. It's a lot to absorb, all this talk of negative energy and Jupiter mass requirements. The universe seems determined to keep its treasures locked away, revealing glimpses of possibility only to slam the door shut with prohibitive costs. But scientists are stubborn creatures. They looked at Alcubierre's work and didn't see a dead end, they saw a starting point. Over the following decades, researcher after researcher would take the basics concept and try to refine it, optimize it, find clever workarounds that might bring the energy requirements down from completely absurd to merely incredibly difficult. The journey from theoretical breakthrough to practical technology is rarely straightforward, and the warp drive was no exception. Some researchers focused on the geometry of the bubble itself, wondering if different shapes might require less exotic matter. Others explored whether the bubble could be made thinner, concentrating the space-time distortion in a narrower shell rather than spreading it across a larger volume. Still others questioned whether the exotic matter needed to be present throughout the entire journey, or only during acceleration and deceleration phases. Each refinement brought the numbers down slightly. Jupiter's worth of exotic matter became Saturn's worth, then Earth's worth, then something more like a star cluster's worth of negative energy. The improvements were real, but incremental, and even the most optimistic projections still required quantities of exotic matter that seemed utterly unattainable with any foreseeable technology. You might wonder why scientists kept working on something that seemed so hopeless. The answer lies in the unique nature of theoretical physics. Unlike engineering, where you need to actually build things, theoretical physics operates in the realm of pure mathematics and possibility. Proving that something is mathematically consistent, that it doesn't violate known laws of physics, is itself a meaningful achievement, even if practical realization remains centuries or millennia away. Besides, physics has a history of surprising us. Concepts that seemed impossible in one era became routine in the next. Perhaps some future discovery would change everything, revealing new physics that made exotic matter accessible or unnecessary. Until then, the dream would be kept alive through equations and simulations, waiting for reality to catch up. Your breathing has grown slower and deeper as you contemplate these patient scientists, tending their impossible gardens in the soil of mathematics, hoping someday the flowers might bloom. The years pass in your drowsy imagination like pages turning in a very specialized academic journal. After Alcubierre's 1994 paper, a small but dedicated community of physicists began the painstaking work of exploring every possible avenue for making warp drives less impossible. You picture them scattered across universities and research institutions worldwide, united by equations and email threads, chipping away at a problem that most of their colleagues considered somewhere between quixotic and crackpot. This is how revolutionary ideas often develop, you realize. Not with fanfare and massive funding, but in quiet corners of academia where curious minds refuse to let go of interesting problems. The warp drive researchers knew their work might never lead anywhere practical. They did it anyway, because the question itself was too fascinating to abandon. One of the first major refinements came from a physicist named Chris van den Broek in 1999. He proposed a clever geometric modification to Alcubierre's original design. Instead of creating a large warp bubble to contain a spacecraft, what if you created a tiny bubble connected to a larger internal volume through a kind of space-time throat? The external surface area of the bubble would be microscopic, requiring far less exotic matter to distort, while the interior could still be large enough to hold passengers. It was like building a house that looked tiny from outside, but contained an impossibly spacious interior, essentially a TARDIS from Doctor Who rendered in the mathematics of general relativity. Here's a mainstream historical fact about the scientific community's reaction. Van den Broek's paper generated significant interest because it demonstrated that the exotic matter requirements weren't fixed. They depended on the specific geometry chosen, and clever choices could reduce them dramatically. His modification brought the energy requirements down from Jupiter masses to about 3 solar masses, still absurdly large, but a reduction of several orders of magnitude nonetheless. Progress was possible. Throughout the 2000s and 2010s, researchers continued finding optimizations. Harold White, a physicist at NASA's Johnson Space Center, proposed that oscillating the intensity of the warp field might reduce energy requirements even further. By making the space-time distortion vary with time rather than remaining static, he argued, you could potentially achieve the same effect with far less exotic matter. His calculations suggested requirements might be reduced to something merely the mass of a spacecraft itself, rather than stellar masses. Now here's a quirky tidbit about how these theoretical refinements got tested. White actually built a small laboratory experiment called the White-Jude warp field interferometer. It wasn't designed to create an actual warp field. The energies involved would be far too small for that. Instead, it was meant to detect extraordinarily tiny space-time distortions, on the order of 1 part in 10 million, that might indicate the experimental setup was on the right track. The results were inconclusive and controversial, with most physicists remaining skeptical that anything meaningful was measured. But the attempt itself demonstrated how seriously some researchers were taking the possibility. Historians still argue whether White's energy estimates were valid or whether they relied on mathematical assumptions that didn't properly translate to physical reality. His work faced criticism from other physicists who suggested he had made errors in his calculations or was being overly optimistic about what the mathematics allowed. This kind of scientific dispute is healthy and normal. Extraordinary claims require extraordinary evidence, and the warp drive community subjected every proposed improvement to rigorous scrutiny. You shift slightly under your covers, your mind wandering through these decades of incremental progress. It must have been frustrating, you think, working on something that seemed perpetually stuck in the realm of theory. Every optimization brought the numbers down, but never quite into the range of feasibility. Every proposed solution created new problems that needed solving. The finish line kept receding, even as researchers ran toward it. And yet, something valuable was being built during these years of patient tinkering. A shared vocabulary developed, a common set of mathematical tools and conceptual frameworks that allowed researchers to build on each other's work. Problems were identified and catalogued, not just the exotic matter issue, but challenges related to creating and destroying warp bubbles, navigating while inside them, and potential hazards like radiation accumulation at the bubble's leading edge. Some researchers began exploring entirely different approaches. What if you didn't need a complete bubble surrounding the spacecraft? What if you could create something more like a wave or a soliton, a self-reinforcing disturbance in space-time that carried a payload along with it? These approaches faced their own challenges, but they represented the kind of creative thinking that keeps scientific fields alive even when progress seems impossibly slow. The warp drive research community also began taking more seriously the question of what happens when you travel faster than light. In conventional physics, superluminal travel creates paradoxes related to causality, the principle that effects should follow causes. We'll explore these paradoxes in detail later, but their existence added another layer of concern to the theoretical framework. Perhaps nature forbids faster-than-light travel, not through energy requirements, but through logical consistency. Perhaps any mechanism that allowed superluminal motion would automatically create time machines and grandfather paradoxes that the universe simply won't permit. By the early 2000s, the field had accumulated decades of theoretical development. Energy requirements had been reduced by many orders of magnitude from Alcubierre's original estimates, though they remained far beyond current technology. Mathematical frameworks had been refined and extended. Potential problems had been identified and in some cases addressed. The foundation was laid for something new, and then, quite recently, a group of researchers proposed something that genuinely shifted the conversation. They asked a question that seems obvious in retrospect, but hadn't been properly explored. What if you don't need exotic matter at all? Your eyes flutter closed as you contemplate this possibility, this potential breakthrough after decades of struggle. The stars behind your eyelids seem to draw slightly closer, as if the universe itself is leaning in to hear what comes next. The year is 2024, and you picture a group of researchers bent over their computers, running simulations and checking equations that might change everything humanity understands about interstellar travel. Their work builds on decades of warp drive research, but takes a fundamentally different approach, one that dispenses with the exotic matter that has plagued the field since Alcubierre's original proposal. The key figures in this new chapter come from the Applied Physics Group, an independent research organisation focused on theoretical physics with practical implications. They've been working on what they call positive energy warp drives, and the name itself hints at what makes their approach revolutionary. Instead of requiring exotic matter with its negative energy density, their proposed configurations use only ordinary matter and energy, the kind that actually exists and that we can, at least in principle, produce and manipulate. You might wonder how this is even possible. After all, physicists spent 30 years assuming exotic matter was essential to the warp drive concept. The answer involves a subtle but crucial distinction in how space-time can be curved. Earlier warp drive designs focused on creating the sharpest possible gradient in space-time curvature, a steep cliff between the contracting region in front and the expanding region behind. This sharp gradient is what demanded exotic matter. But what if you allowed for gentler, more gradual distortions? What if you were willing to accept a slightly less efficient drive in exchange for using only materials that actually exist? Here's a mainstream historical fact that provides context for this breakthrough. General relativity has always permitted an enormous variety of space-time geometries, most of which have never been seriously explored. Physicists tended to focus on solutions with specific properties: spherical symmetry, maximal efficiency, mathematical elegance. The positive energy warp drives emerge from a more systematic exploration of the solution space, asking what configurations might be achievable rather than what configurations might be optimal. The mathematics is dense, but the conceptual framework is surprisingly accessible. Imagine space-time as a flowing river rather than a static landscape. In this picture, a warp drive doesn't push a spacecraft through stationary space. It creates a current that carries the spacecraft along. The Alcubierre drive created this current using exotic matter to generate an impossibly steep slope in the river. The new approach creates a gentler current using only conventional matter, like redirecting a river by piling up rocks rather than by magically creating a negative rock that repels water. Now here's a quirky tidbit about how this research came together. The applied physics team deliberately took an interdisciplinary approach, bringing together expertise in general relativity, quantum field theory, and engineering to attack the problem from multiple angles simultaneously. This kind of collaboration is increasingly common in cutting-edge physics, but remains somewhat unusual in the traditionally siloed world of theoretical research. They treated the warp drive not as a purely mathematical curiosity, but as an engineering challenge to be solved, a subtle shift in mindset that opened up new possibilities. Historians still argue whether the positive energy warp drive represents a genuine breakthrough, or merely a different set of trade-offs that might prove equally impractical. Some physicists point out that even with ordinary matter, the energy requirements remain astronomical by current standards. Others suggest the new approach might face different but equally severe obstacles related to stability, control, or fundamental physics we don't yet understand. The field is too young, and the research too new for definitive judgments. What's striking about the new proposal is how it reframes the entire conversation around faster-than-light travel. For decades, the discussion centered on whether exotic matter could exist and whether we could ever produce enough of it. Now, suddenly, the conversation shifts to engineering questions. How do we generate and focus the required energy? How do we shape the space-time distortion with sufficient precision? How do we maintain stability throughout the journey? These are still incredibly difficult questions, but they're different in character. They're about capability rather than possibility. You feel a subtle excitement building beneath your drowsiness, like a distant melody you can almost hear. This is how scientific revolutions often begin, not with dramatic announcements, but with quiet shifts in what questions are being asked. The positive energy warp drive might ultimately prove impractical for reasons we don't yet understand. But even its existence as a theoretical possibility changes the landscape of what humanity might someday achieve. The researchers' papers outline several variations on the basic theme, each with different characteristics and requirements. Some configurations would create bubbles that move slightly faster than light. Others might reach multiples of light speed. Some would be more energy efficient but harder to control. Others would be more stable but require more power. It's a menu of options, a toolkit for future engineers to draw from once the fundamental technology becomes available. One particularly interesting aspect of the new work involves the relationship between the warp bubble and the objects inside it. In earlier designs, the interior of the bubble was completely isolated from the exterior. Passengers would experience normal space-time and have no way to observe or interact with the distorted space around them. The positive energy design suggests this might not be strictly necessary. Perhaps partial bubbles, open configurations, or hybrid approaches could achieve similar effects with different trade-offs. The applied physics team has been careful to emphasize the limitations of their work. They're proposing theoretical frameworks, not actual spacecraft designs. The gap between equations on paper and hardware in space remains enormous. But they've also been deliberate about outlining what intermediate steps might look like, what technologies would need to be developed, what experiments might test the underlying physics, what milestones might mark progress toward eventual implementation. You breathe slowly and steadily, imagining laboratories of the future where engineers calibrate space-time distortion fields with the same precision that today's engineers calibrate microchips. The stars outside your window don't seem quite so unreachably distant anymore. The soft glow of your imagination illuminates equations floating in darkness, each symbol representing some aspect of curved space-time. You're trying to understand what makes these new positive energy warp bubbles work, and while the mathematics is beyond what most humans will ever grasp, the core concepts are surprisingly approachable when translated into everyday language. Start with what energy means in this context. When physicists talk about positive versus negative energy density, they're describing how a region of space contributes to the overall gravitational field. Positive energy, the kind you find in ordinary matter, light and electromagnetic fields, curves space-time in familiar ways. It causes gravity, attracts other matter, behaves exactly as you'd expect from everyday experience. The sun's positive energy bends light from distant stars, a phenomenon that Einstein predicted and astronomers confirmed during a solar eclipse in 1919. Here's a mainstream historical fact about that famous eclipse observation. The British astronomer Arthur Eddington led the expedition that photographed stars during totality, finding their apparent positions shifted by exactly the amount Einstein's equations predicted. This was one of the first experimental confirmations of general relativity and made Einstein a worldwide celebrity overnight. It demonstrated that space-time curvature wasn't just a mathematical abstraction. It was physical reality that affected the paths of light beams. Negative energy, by contrast, would curve space-time in the opposite direction. It would create gravitational repulsion rather than attraction. If you had a lump of exotic matter, it wouldn't pull you toward it. It would push you away. The Alcubierre drive required enormous quantities of this stuff to create the asymmetric bubble that would allow faster-than-light travel. Contracting space in front required one type of curvature. Expanding space behind required another. The combination demanded both positive and negative energy, carefully arranged. The breakthrough in positive energy warp drives comes from recognizing that you don't necessarily need this sharp contrast. Instead of creating regions of expansion and contraction side by side, you can create a more gradual flow of space-time that carries a payload along without requiring the forbidden ingredient. Think of it like the difference between creating a waterfall, which requires a dramatic height difference, and creating a gentle stream, which only requires a slight slope. Both move water from one place to another. One does it dramatically and efficiently, while the other does it gradually and sustainably. Now here's a quirky tidbit about how physicists discovered this possibility. Much of the key insight came from studying phenomena called solitons, waves that maintain their shape while travelling at constant speed. Solitons appear in many areas of physics, from ocean waves to fibre optic communications to quantum field theory. The mathematics that describes them turned out to be applicable to certain space-time geometries, suggesting that stable, self-maintaining warp configurations might exist even without exotic matter. Historians still argue whether the soliton analogy captures the full physics, or whether it's merely a useful pedagogical tool that glosses over important complications. Some researchers believe the connection is deep and fundamental. Others suggest it's a helpful metaphor that might lead us astray if taken too literally. These kinds of debates are healthy signs of an active research field working through the implications of new ideas. The practical upshot of all this mathematics is that space-time can potentially be persuaded to carry a spacecraft along without requiring any material to move faster than light locally. Inside the warp bubble, the spacecraft and its passengers are essentially stationary relative to the space immediately surrounding them. That space, however, is moving relative to the distant stars. It's like standing on an escalator. You're not climbing stairs, but you're still ascending. The escalator is doing the work. This distinction is crucial for understanding why positive energy warp drives don't violate special relativity. The light speed limit applies to motion through space, not motion of space itself. When galaxies recede from us faster than light due to cosmic expansion, nothing is violating any physical law. Space itself is stretching. A warp drive would exploit the same loophole on a controlled local scale. The energy requirements for positive energy warp drives, while not infinite, remain substantial. Current estimates suggest you might need the energy output equivalent to a small star focused into a precisely configured shell around your spacecraft. This is obviously beyond anything humanity can currently produce, but it's not beyond what physics allows. It's a matter of capability, not principle, a significant distinction that separates engineering challenges from fundamental impossibilities. You find yourself contemplating what these energy scales actually mean. Humanity's total energy production is a fraction of what the sun outputs in a second. To power a warp drive with current technology would be laughably impossible. But energy production has grown exponentially throughout human history, from fire to coal to nuclear to solar. If that trend continues for another few centuries, the numbers might start to look different. The researchers who developed these positive energy frameworks are careful to distinguish between different phases of potential development. Near-term work would focus on validating the theoretical foundations, designing experiments that might test predictions at small scales, and refining the mathematics to optimize configurations. Medium-term work might involve prototypes that distort space-time measurably, even if the effects are tiny. Long-term work, decades or centuries away, might finally produce drives capable of interstellar travel. You settle more deeply into your pillow, the equations fading into a gentle background hum of possibility. The universe's rules are strict but not entirely unforgiving. With enough cleverness and enough energy, perhaps the cosmos will yield its treasures after all. You're floating now, somewhere between wakefulness and dreams, and your mind turns to pictures rather than numbers. Because understanding warp drives ultimately requires visualizing something that human brains never evolved to comprehend: the shape of curved space-time. We're creatures of three-dimensional space and linear time, and asking us to imagine four-dimensional geometry is like asking a fish to understand mountains. But physicists have developed analogies that help bridge the gap. The most famous is the rubber sheet analogy, and you've probably encountered it before. Imagine stretching a sheet of rubber flat, like the surface of a trampoline. Now place a heavy ball, say a bowling ball, in the centre. The rubber deforms, creating a depression around the ball. If you roll a marble across the sheet, it curves toward the depression, spiralling inward. This is supposed to represent how massive objects curve space-time and create gravity. Here's a mainstream historical fact about the limitations of this analogy. Physicists have criticised it almost since it was invented, noting that it already assumes gravity in order to work. The bowling ball creates a depression because Earth's gravity pulls it downward. You can't really use gravity to explain gravity. And the analogy only depicts two spatial dimensions plus the downward direction, missing crucial aspects of how four-dimensional space-time actually curves. Still, for building intuition, it's the best tool we have. For warp drives, you need to modify this picture. Imagine the rubber sheet stretching dynamically, contracting in one direction while expanding in another. In front of the warp bubble, the sheet bunches up, bringing distant points closer together. Behind the bubble, the sheet stretches out, pushing points further apart. The spacecraft rides in a little dimple that stays flat, normal space, while the distortions happen all around it. Now here's a quirky tidbit about attempts to visualize this more accurately. Some physicists have created animations and even virtual reality simulations showing what the view from inside a warp bubble might look like. The results are strange and beautiful. Ahead of you, stars would appear blue-shifted and compressed into an intense ring of light. Behind you, stars would be red-shifted and stretched. The distortion would look something like flying through a tunnel where the walls are made of light itself. It's quite different from the smooth star lines of science fiction movies. Historians still argue whether these visualizations capture the subjective experience of warp travel, or whether the reality would be even stranger than our simulations suggest. Some physicists point out that the extreme space-time curvature near the bubble's edge might create visual effects we can't even properly render with current technology. Others suggest the interior would be surprisingly ordinary. A comfortable cabin where passengers barely notice the reality-bending physics just outside. Another helpful picture involves flowing rivers. Imagine space as a river flowing toward you. If you swim against the current at exactly the speed of the water, you stay in place relative to the riverbed. If the current speeds up, if space starts flowing toward you faster than you can swim, you'll be carried backward no matter how hard you try. This is what happens at the event horizon of a black hole. Space falls inward faster than light can escape. A warp drive reverses this picture in a controlled way. Instead of space falling into a singularity, space flows past the spacecraft in the direction of travel. If that flow is faster than light, the spacecraft moves faster than light relative to distant observers, even though locally nothing is exceeding any speed limit. It's surfing on space-time rather than swimming through it. The positive energy warp drives create this flow using massive concentrations of ordinary energy, shaped into shells or tori or other geometric configurations around the spacecraft. The specific shape matters enormously. Different geometries produce different flow patterns, different efficiencies, different stability characteristics. It's like the difference between a streamlined submarine and a box with propellers. Both can move through water, but one does it much more elegantly. You might wonder what it would feel like to be inside one of these bubbles. The mathematics suggests surprisingly little. No acceleration, no sensation of motion, no dramatic forces pushing you against your seat. The spacecraft and everything inside it would be in free fall, following the natural paths through the local space-time. You might feel nothing at all, just floating peacefully, while the universe rearranges itself around you. This absence of physical sensation is actually important for practical warp drive design. Conventional acceleration to relativistic speeds would crush any biological passenger. The forces involved would be lethal long before you approach light speed. But inside a warp bubble, you're not accelerating in the conventional sense. The space around you is changing, not your motion through it. It's the difference between being pressed into your airplane seat during takeoff and being carried along by a gentle tide. The gentle curvature of your pillow against your cheek mirrors, in some small way, the gentle curvature of space-time in these optimized warp designs. Both yield to accommodate what rests against them. Both create comfort through careful shaping. The universe, despite its vast indifference to human concerns, occasionally permits configurations that fragile beings might survive. Your breathing has become slow and rhythmic as you drift through these pictures, the rubber sheets and flowing rivers blending into a seamless dreamscape of bent space. Somewhere ahead, the stars wait patiently. The loophole, you realize as you drift deeper into relaxation, has been hiding in plain sight all along. Einstein's equations never said faster-than-light travel was impossible. They said faster-than-light motion through space was impossible. This distinction between moving through space and moving with space is the key to everything. Let's make this absolutely concrete because it matters. When you accelerate a rocket, you're pushing against the fabric of space-time, imparting momentum to your spacecraft relative to the space around you. The faster you go, the more energy it takes to go faster still. At the speed of light, the energy required becomes infinite, a hard wall that no amount of thrust can overcome. Your velocity through space is limited by the fundamental structure of how space and time relate to each other. Here's a mainstream historical fact that illustrates this beautifully. Particle accelerators routinely push protons and electrons to 99.9999% of light speed. At these velocities, the particle's effective mass increases thousands of times over their rest mass, requiring enormous magnetic fields and tremendous energy to bend their paths and keep them accelerating. The Large Hadron Collider, the most powerful particle accelerator ever built, still cannot push particles to actual light speed, and it never will. The energy requirements grow without bound as you approach that limit. But here's the elegant escape. Space itself isn't bound by these restrictions. Space can expand or contract at any rate whatsoever, without violating relativity. During the first fractions of a second after the Big Bang, the universe expanded far faster than light. Today, distant galaxies recede from us at superluminal speeds due to cosmic expansion. No law is broken because nothing is moving through space faster than light. Space itself is stretching, carrying the galaxies along with it. A warp drive exploits this same principle. You don't accelerate through space, you modify space itself so that it carries you along. Your velocity through your local space remains zero, or at least subliminal. But your location relative to distant stars changes faster than light, because the space between you and those stars has been manipulated. It's the ultimate semantic loophole, but the universe doesn't care about semantics. The mathematics works either way. Now here's a quirky tidbit that speaks to the strangeness of this concept. Some physicists initially rejected Alcubierre's work precisely because it seemed too much like cheating. The whole point of the light speed limit, they argued, was to prevent faster-than-light travel and the paradoxes it might create. Finding a loophole felt like discovering that the speed limit on a highway doesn't apply if you're technically standing still on a moving platform. The spirit of the law seemed violated even if the letter wasn't. But physics doesn't care about spirit versus letter. It cares about what the equations allow. Historians still argue whether nature intended this loophole, or whether it's an artifact of our incomplete understanding. Some physicists believe that a complete theory of quantum gravity will close the loophole, revealing new physics that forbids warp drives just as surely as conventional physics forbids faster-than-light rockets. Others suggest the loophole is fundamental, a genuine feature of how space-time works that future civilizations might exploit. The debate cannot be settled until we understand quantum gravity better. The practical implications of this distinction are profound. If warp drives are possible, interstellar travel becomes qualitatively different from anything we've previously imagined. The journey to Alpha Centauri, our nearest stellar neighbour at 4 light-years distance, could potentially take days or weeks rather than millennia. The entire galaxy, spanning 100,000 light-years, might become accessible within human timescales rather than remaining forever beyond reach. More importantly, the occupants of a warp-drive spacecraft would experience normal time flow. Unlike near-light-speed travel, where time dilation creates devastating separations between travellers and those they leave behind, warp travel would preserve synchronicity. You could visit distant stars and return to find your home and family essentially unchanged. This transforms interstellar exploration from a one-way diaspora into something more like conventional travel. Ambitious and adventurous, certainly, but not an irreversible exile. You feel a warmth spreading through you that has nothing to do with your blankets. It's the warmth of possibility, of hope that the universe might not be as lonely as it sometimes appears. The stars outside your window seem friendlier now, potential destinations rather than unreachable lights. Perhaps humanity's children, or their children's children, will actually walk beneath alien suns. The mathematics doesn't lie. The loophole exists. The only questions now are practical ones. Can we generate enough energy? Can we shape it precisely enough? Can we create stable configurations that don't collapse or run away? These are formidable challenges, but they're engineering challenges. They're problems that might have solutions. You smile softly in the darkness, grateful for this elegant cosmic backdoor. The universe sets rules, but it also apparently leaves room for clever travellers who read the fine print carefully enough. Your smile fades slightly as you remember that theoretical possibility and practical reality are separated by vast chasms of engineering difficulty. The mathematics of positive energy warp drives may work out, but actually building one of these things would require capabilities so far beyond current technology that they barely seem like the same species of problem. Start with energy production. The most optimistic estimates for positive energy warp drives suggest requirements on the order of stellar output, the energy released by the sun in some period of time. Current human civilization produces roughly 1/10 of the sun's power output. To scale up by 10 billion times would require revolutionary advances in energy generation. Perhaps fusion power perfected and scaled to enormous facilities. Perhaps orbital solar collectors harvesting energy directly from the sun. Perhaps technologies we haven't even imagined yet. Here's a mainstream historical fact that puts this challenge in perspective. Humanity's total annual energy consumption is roughly equivalent to the energy released by a single hurricane over a few days. We're still learning to harness planetary-scale energy flows, let alone stellar ones. The gap between where we are and where we need to be isn't measured in decades of progress. It might be measured in centuries or millennia. And energy is just the beginning. You'd also need to shape that energy into precise configurations, shells or tori or more complex geometries surrounding your spacecraft, generating exactly the right space-time distortions to create a stable warp bubble. The tolerances involved are likely to be extraordinarily fine. A slight asymmetry might destabilize the bubble entirely. A miscalculation might send you careening off course or trap you inside a configuration you can't escape. Now here's a quirky tidbit about the materials challenge. No known material could survive the stresses involved in generating or maintaining a warp field. The energy densities required would vaporize any conventional structure. Some researchers have speculated about using magnetic confinement, similar to fusion reactor designs, to shape the field without physical contact. Others suggest that advanced metamaterials, engineered substances with properties not found in nature, might offer solutions. These are ideas rather than blueprints, possibilities rather than plans. Historians still argue whether transformational technologies like warp drives develop through steady incremental progress or through revolutionary breakthroughs that change everything at once. The history of flight supports both interpretations. The Wright brothers built on centuries of aerodynamic theory and practical glider experiments, but their powered flight was still a revolutionary moment that changed the pace of development overnight. Perhaps warp drive will follow a similar pattern, long preparation followed by sudden leap. There are also stability questions that remain largely unresolved. A warp bubble is an inherently artificial configuration of space-time, maintained against its natural tendency to relax into flatness. What happens if the maintaining mechanism fails? Does the bubble simply dissipate, leaving the spacecraft stranded in normal space? Or does it collapse violently, potentially destroying everything inside? Some theoretical analyses suggest the bubble's edges would emit intense radiation. Hawking radiation amplified by the extreme space-time curvature. Passengers might be cooked alive even as they travel. Navigation presents its own puzzles. Inside a warp bubble, you're essentially cut off from the universe outside. Light from ahead of you can't reach you normally, because the contracting space distorts its path. You'd be flying blind at superluminal speeds through a galaxy full of stars, planets, asteroids, and other hazards. How do you steer? How do you know where you're going? Some researchers have proposed using quantum entanglement for communication across the bubble boundary, but this introduces new theoretical complications. Then there's the question of creating and dissolving the bubble. You need to start from normal space, generate the warp configuration around yourself, travel to your destination, and then safely return to normal space. Each transition involves complex dynamics that aren't fully understood. The Alcubierre bubble, in its original formulation, required matter outside the bubble to create it, which raised the awkward question of how you could ever initiate the bubble from inside. Positive energy designs may face similar chicken and egg problems. You find these challenges oddly comforting rather than discouraging. They're concrete, specific problems rather than vague impossibilities. Engineers love concrete problems. Given enough time and resources, concrete problems tend to get solved. The pyramids seemed impossible until they were built. The atomic bomb seemed impossible until it exploded. The moon landing seemed impossible until footprints marked the lunar dust. The key word there is time. Warp drives won't be built in your lifetime, or your children's lifetime, or probably even the next several generations. This is a project for future centuries, not future decades. The researchers working on it today are planting seeds whose trees they'll never see, let alone the fruit those trees might bear. Your breathing has slowed almost to the rhythm of a sleeping person, but a small part of your mind stays awake to appreciate this long perspective. Humanity thinks in years and elections. The universe thinks in eons. Perhaps learning to think in longer spans is part of what it takes to become a truly interstellar civilization. You might expect that quantum mechanics, with all its famous weirdness, would make faster-than-light travel harder rather than easier. After all, quantum physics adds restrictions and complications to nearly everything else. But here's a lovely surprise. In the quest for warp drive, quantum mechanics might actually be an ally rather than an obstacle. The connection runs through something called vacuum energy, and it's one of the strangest concepts in all of physics. Empty space, it turns out, isn't really empty. Even in a perfect vacuum, a region with all matter and radiation removed, quantum field theory predicts a seething foam of virtual particles constantly popping into existence and annihilating each other. These particles exist for such brief moments that they can't be directly observed, but their effects are measurable. Here's a mainstream historical fact about how we know vacuum energy is real. The Casimir effect, first predicted in 1948 and experimentally confirmed in 1997, demonstrates that empty space has measurable properties. When two metal plates are placed extremely close together, separated by only nanometers, they experience a tiny attractive force. This force arises because the virtual particles between the plates are constrained by the boundaries, creating a pressure difference with the unrestricted space outside. The vacuum literally pushes the plates together. This matters for warp drives because the Casimir effect creates a region of negative energy density between the plates. Not much, tiny amounts by any macroscopic standard, but real negative energy nonetheless. This is the only known physical mechanism that reliably produces the kind of exotic energy that Alcubierre's original warp drive required. It suggests that exotic matter isn't merely a mathematical fiction, but something that quantum mechanics allows under specific conditions. Now here's a quirky tidbit about attempts to scale up the Casimir effect. Some researchers have proposed constructing nested layers of conducting surfaces at nanometer separations, hoping to amplify the negative energy density. The results have been discouraging. The effect remains stubbornly microscopic no matter how cleverly you arrange the plates. But the attempts themselves represent a kind of experimental reconnaissance, mapping out what quantum mechanics permits and what it forbids. Historians still argue whether the Casimir effect provides a genuine pathway toward exotic matter, or whether it's merely a tantalizing hint that leads nowhere practical. Some physicists believe that quantum field theory contains deeper mechanisms for generating negative energy that we haven't discovered yet. Others suggest the weak energy conditions, theorems that seem to limit negative energy density, will ultimately prove robust, closing this avenue for warp drives. The debate continues in academic journals and conference presentations. The quantum vacuum also connects to dark energy, the mysterious force accelerating the universe's expansion. Dark energy behaves like a cosmological constant, a uniform energy density throughout all of space that creates repulsive gravity. While dark energy isn't the same as the exotic matter needed for warp drives, its existence proves that the universe allows configurations that drive expansion against gravitational attraction. Perhaps similar physics, properly understood and controlled, could be harnessed for propulsion. Some researchers have explored the interface between general relativity and quantum field theory, specifically in the context of warp drive stability. Classical general relativity allows warp bubbles as solutions to Einstein's equations. But what happens when you include quantum effects? Does the bubble radiate energy and collapse? Does it create instabilities that grow out of control? Does it produce particles at rates that become dangerous? These questions require quantum gravity to answer fully, and quantum gravity remains physics' great unsolved problem. There are also speculative connections to other quantum phenomena. Entanglement, the strange correlation between particles that persists regardless of distance, has sometimes been proposed as a mechanism for communication across warp bubble boundaries. The no communication theorem proves you can't use entanglement to send information faster than light, but inside a warp bubble, the rules might be different. The entangled particles would technically be at rest relative to each other, only the space between them would be moving. Whether this creates a loophole in the no communication theorem remains an open question. Quantum tunneling offers another metaphorical inspiration. Particles routinely traverse barriers that classical physics insists they cannot cross, appearing on the other side as if the barrier didn't exist. The universe apparently permits shortcuts under the right conditions. Perhaps space-time itself allows shortcuts under conditions we haven't learned to create yet. You nestle deeper into your blankets, the soft warmth wrapping around you like quantum fluctuations fill the void of space. Both are invisible, intangible, yet powerfully present. The universe at its most fundamental level seems to contain hidden resources, potential energies lying dormant until the right conditions unlock them. The marriage of quantum mechanics and general relativity remains incomplete, a theoretical gap that physicists have struggled to close for nearly a century. But in that incompleteness lies possibility. Perhaps the final theory, when we find it, will reveal pathways to energy manipulation we can barely imagine today. Perhaps the strange behavior of the quantum vacuum, properly understood, will prove to be humanity's ticket to the stars. Your eyelids grow heavier as you contemplate these quantum whispers of encouragement. The universe is strange, and sometimes strangeness works in our favour. The Casimir effect deserves a closer look, because it's the closest thing we have to experimental evidence that the physics underlying warp drives might actually work. You're lying there in the darkness, and you can imagine two impossibly thin metal plates suspended in a vacuum chamber, separated by a gap so narrow that light itself can barely squeeze through. At separations of a few hundred nanometers, less than 1,000th the width of human hair, something remarkable happens. The plates experience an attractive force pulling them together, a force that can't be explained by any conventional mechanism. It's not electromagnetic, not gravitational, not any of the usual suspects. It's something stranger, a pressure exerted by the quantum vacuum itself. Here's a mainstream historical fact about the discovery of this effect. Dutch physicist Hendrik Casimir predicted it in 1948 while working on the theory of molecular forces at the Philips Research Laboratory. He was trying to understand why colloidal particles in certain solutions attracted each other more strongly than the electromagnetic theory predicted. The answer led him to consider how the quantum vacuum might behave differently in confined spaces, a question nobody had seriously asked before. The experimental confirmation took nearly 50 years. Measuring forces at the nanonewton scale between surfaces separated by nanometer gaps is extraordinarily difficult. Dust particles, surface roughness, electrostatic charges, any of these could swamp the tiny Casimir force. Finally, in 1997, physicist Steve Lamoureux achieved a precision measurement that matched Casimir's prediction to within 5%. The quantum vacuum's strange behaviour had been confirmed. What makes this relevant to warp drives is the nature of the force. Between the plates, the quantum vacuum has less energy density than the vacuum outside. This difference creates the attractive force. The outside vacuum effectively pushes the plates together. And here's the crucial point. A region with less energy than empty space has, by definition, negative energy density. The Casimir effect creates tiny pockets of the exotic physics that warp drives would need to exploit. Now here's a quirky tidbit about attempts to amplify this effect. Some researchers have experimented with different geometries, wondering if shapes other than flat plates might produce stronger effects. Spherical cavities, cylindrical tubes, corrugated surfaces, each geometry creates different boundary conditions for the quantum fields, potentially enhancing or suppressing the Casimir force. The results have been mixed, with some configurations producing slightly stronger effects, but nothing approaching the magnitude needed for practical applications. Historians still argue whether the Casimir effect represents a genuine pathway to exotic matter, or an interesting dead end. Optimists point out that we're still in the early days of understanding quantum vacuum phenomena. Future discoveries might reveal amplification mechanisms we can't currently imagine. Pessimists note that the effect seems fundamentally limited by quantum mechanics itself, unable to produce the sustained, large-scale negative energy densities that warp drives would require. The energy densities involved are instructive. The Casimir force between plates separated by 100 nanometers corresponds to a negative energy density of roughly 1 joule per cubic meter. That sounds like something, but remember that warp drives might require negative energy equivalent to stellar masses concentrated in relatively small volumes. The gap between what the Casimir effect provides and what warp drives need spans many orders of magnitude, like comparing a candle's heat to a nuclear explosion. But here's the thing about small effects. They often point the way toward bigger ones. The first nuclear reactions released tiny amounts of energy, less than a watt, but they proved the principle that eventually led to power plants and bombs. The first lasers were scientific curiosities with no practical applications. Now they're everywhere. Perhaps the Casimir effect is similarly a proof of concept rather than a final destination. Some theorists have explored whether the Casimir effect might be enhanced by using superconducting materials, extremely strong electromagnetic fields, or other exotic conditions. The quantum vacuum isn't a fixed background. It responds to its environment. Different field configurations might coax it into producing stronger effects. This research is speculative, but not entirely without foundation. Quantum field theory definitely allows for vacuum states with unusual properties under unusual conditions. There's also the question of dynamic Casimir effects. What happens when the plates move? Rapidly oscillating one of the plates can actually create real photons out of the vacuum, converting the zero-point energy into observable radiation. This was confirmed experimentally in 2011 using a microwave cavity with a superconducting quantum interference device. If we can extract energy from the vacuum dynamically, perhaps we can manipulate its other properties as well. You find yourself thinking about these tiny plates, invisibly close together in some laboratory vacuum chamber, experiencing forces that arise from the fundamental structure of empty space. It's a gentle intimacy between matter and void, a whispered conversation about what reality allows. The Casimir effect reminds us that the universe is stranger than common sense suggests. Space is not nothing, it's something, filled with potential and activity we're only beginning to understand. Perhaps in that strangeness lies the key to crossing the cosmic distances that seem so impossibly vast. Your breathing has become soft and regular, like a tide flowing in and out, like virtual particles appearing and vanishing in the quantum foam. Let's take a break from equations and vacuum chambers to remember something important. Humans have a remarkably poor track record of knowing what's truly impossible. You're lying there in the comfortable darkness, and your mind wanders through history, finding example after example of experts confidently declaring something beyond the realm of possibility, only to be proven spectacularly wrong. In 1895, Lord Kelvin, one of the most distinguished physicists of his era, allegedly declared that heavier-than-air flight was impossible. Within 8 years, the Wright brothers flew at Kitty Hawk. The specific attribution to Kelvin is disputed by historians, but the sentiment was widespread among respected scientists of the time. The physics of flight was poorly understood, and the engineering challenges seemed insurmountable. Here's a mainstream historical fact about the rapid transformation that followed. Just 66 years elapsed between the Wright flyers' 12-second hop and Apollo 11's landing on the moon. A single human lifetime spanned the entire journey from first flight to lunar exploration. Your grandparents might have been born in a world without airplanes and lived to watch astronauts bounce across another world's surface on television. Nuclear energy faced similar skepticism. In 1933, the great physicist Ernest Rutherford, who discovered the atomic nucleus, dismissed the idea of extracting useful energy from atoms as moonshine. Less than a decade later, the first nuclear chain reaction was achieved. Within 2 decades, nuclear power plants were generating electricity. The transition from obviously impossible to routine technology happened within the career span of scientists who had personally declared it couldn't be done. Now here's a quirky tidbit about skepticism towards spaceflight specifically. In 1956, the British astronomer royal, Richard Woolley, declared that space travel was utter bilge. Exactly 1 year later, the Soviet Union launched Sputnik, and the space age began. Woolley spent the rest of his career being reminded of this prediction. The universe seems to take particular pleasure in humbling those who confidently draw boundaries around what's possible. Historians still argue whether these examples teach us that nothing is truly impossible, or whether they merely show that prediction is difficult and experts are often wrong about specific timelines. After all, for every technology that succeeded despite skepticism, there are others. Perpetual motion machines, faster-than-light communication via tachyons, that remain impossible no matter how much optimism we apply. The challenge is distinguishing between premature skepticism and well-founded doubt. What's striking about the warp drive case is that the objections have shifted over time. In Alcubierre's day, the main objection was the exotic matter requirement, physics that might not exist at all. Now, with positive energy warp drives, the objection is primarily about scale. Physics that definitely exist but that we can't currently manipulate at the necessary magnitude. That's a significant evolution in the nature of the problem. Consider how other impossible technologies developed. Heavier-than-air flight required understanding aerodynamics, developing suitable materials, and building engines with sufficient power-to-weight ratios. Each component advanced separately through multiple fields of engineering and science. When the pieces finally came together, flight became possible almost suddenly. Warp drives might follow a similar pattern. Advances in energy generation, metamaterials, quantum field manipulation, and space-time physics might each proceed independently for decades or centuries. Then, perhaps, some future generation will find that all the pieces have accumulated, waiting to be assembled. What seems impossibly far off from our current vantage point might feel nearly inevitable from theirs. There's also the possibility of unexpected discoveries that change the landscape entirely. Einstein didn't set out to discover relativity because he wanted to find loopholes in the light speed limit. He was solving puzzles about electromagnetism and found something profound. Future physicists pursuing their own curiosities might stumble upon phenomena that make warp drives easier, or might confirm that they're truly impossible after all. You think about the dreamers throughout history who looked at the stars and imagined travelling among them. They had no technical framework, no understanding of the physics involved, just an intuition that somehow, someday, it might be possible. Most of them were wrong about the details. All of them were right about the human drive to explore, to push beyond current limitations, to refuse to accept impossible as a final answer. The blankets around you feel like a cocoon, protective and warm. Inside this cocoon, you're safe from the cold certainties that might otherwise crush hope. Inside this cocoon, you can dream of futures where the impossible becomes routine, where the stars are destinations rather than decorations. Perhaps you're engaging in wishful thinking. Perhaps the physics truly forbids what you're imagining, and no amount of cleverness will find a loophole. But humans have been wrong about truly forbids so many times before that the phrase has lost some of its authority. The history of technology is largely a history of imagination outrunning expert opinion. To appreciate why faster-than-light travel matters so much, you need to feel, not just intellectually understand, just how vast the distances between stars truly are. You're drifting towards sleep, and numbers float through your consciousness, each one more humbling than the last. The Moon, humanity's only extraterrestrial destination, is about 384,000 kilometers from Earth. At highway speeds, it would take roughly 6 months to drive there. The Apollo astronauts made the journey in 3 days, a remarkable achievement of engineering and courage. Mars, the next target for human exploration, averages about 225 million kilometers away. At the speed of the Apollo spacecraft, that journey would take months. Current mission plans involve travel times of 6 to 9 months each way, with astronauts spending years away from Earth for missions that explore a neighbour so close it sometimes appears as a bright reddish dot in our evening sky. Here's a mainstream historical fact that illustrates how recently these distances became real to human experience. Before the space age, the moon was genuinely otherworldly, unreachable, mythological. People had looked up at it for all of human history without any expectation of ever going there. Then, within a single decade, the 1960s, it went from fantasy to reality. But even that dramatic leap covered only the tiniest fraction of cosmic distances. The Sun sits about 150 million kilometers from Earth, close enough that its light reaches us in 8 minutes. The nearest star, Proxima Centauri, is roughly 40 trillion kilometers away, about 270,000 times farther than the Sun. Its light takes over 4 years to reach us. If you scaled the solar system down so that the Earth-Sun distance was 1 inch, Proxima Centauri would be over 4 miles away. Now here's a quirky tidbit about what these distances mean for communication. If you sent a radio message to a hypothetical civilization at Proxima Centauri, you'd wait over 8 years for a reply, 4 years there, 4 years back. A conversation would span decades. Coordinating any kind of joint activity across such distances, using light-speed communication, would be essentially impossible. Historians still argue whether early space visionaries truly understood the implications of interstellar distances, or whether they glossed over the difficulties in their enthusiasm. Some science fiction of the mid-20th century assumed we'd be visiting other stars by now, extending the rapid progress of the space age outward indefinitely. Reality has been considerably more stubborn. The Milky Way galaxy spans roughly 100,000 light-years. Even at the speed of light, crossing from one side to the other would take 100 millennia. Our galaxy contains somewhere between 100 and 400 billion stars, many with planetary systems of their own. The sheer number suggests that life, possibly even intelligent life, might be common. But the distances ensure that even if the galaxy teems with civilizations, they might remain forever isolated from each other, trapped in their own stellar neighborhoods. Beyond our galaxy lie others, billions of them, stretching across an observable universe roughly 93 billion light-years in diameter. The most distant objects we can see are so far away that their light has been traveling since near the beginning of time itself. These distances aren't just large, they're conceptually overwhelming. Scales that the human brain never evolved to process because they are utterly irrelevant to survival on an African savanna. Consider what faster-than-light travel would mean against this backdrop. Even a modest warp drive, one that could sustain 10 times light speed, would transform interstellar travel from impossible to merely difficult. Proxima Centauri would be roughly 5 months away rather than 40 millennia. The trip to the centre of the galaxy would take centuries rather than tens of thousands of years, still beyond individual human lifespans, but within the reach of civilizational projects. A warp drive capable of 1,000 times light speed would shrink the galaxy to human scales. The whole Milky Way could be crossed in a century. Colonies could be established, maintained, coordinated. Humanity could genuinely become a galactic civilization rather than remaining forever confined to one small planet, orbiting one ordinary star in one spiral arm of one galaxy among billions. You feel the scale of these numbers pressing down on you like a gentle weight, a cosmic perspective that makes everyday concerns seem tiny, and yet, paradoxically, you also feel a strange hope. Because if warp drives are possible, even distantly theoretically possible, then these vast distances might not be eternal barriers. They might be merely temporary obstacles, challenges to be overcome by descendants, who will look back on our era as we look back on those who thought heavier-than-air flight was impossible. The stars outside your window are very far away, but perhaps not forever unreachable. Your imagination begins to stretch toward what a civilization with warp capability might actually look like. The implications cascade through every aspect of human existence, transforming not just technology but culture, politics, philosophy, and perhaps biology itself. Start with the most obvious: colonization. If you can reach other star systems within human lifetimes, you can establish permanent settlements on worlds orbiting distant suns. The search for habitable planets has already revealed thousands of candidates, worlds roughly Earth-sized, orbiting in their stars' habitable zones, potentially harbouring liquid water and the chemistry of life. With warp drive, these statistical abstractions become potential homes. Here's a mainstream historical fact about how colonial expansion has shaped human history. The development of ocean-crossing ships transformed civilization in ways the early shipbuilders never anticipated. New crops, new ideas, new cultures flowed across oceans. Populations migrated and mixed. Diseases spread, empires rose and fell, and the entire trajectory of human development shifted. Interstellar colonization might prove equally transformative, but at scales that dwarf anything in previous experience. Imagine a humanity spread across dozens or hundreds of worlds, each developing its own culture, its own adaptations to local conditions, its own evolutionary path. On high-gravity worlds, humans might become shorter and more muscular. On low-gravity worlds, taller and more delicate. On worlds with different day lengths, different atmospheric compositions, different radiation environments, populations might diverge in ways we can barely predict. Now here's a quirky tidbit about the philosophical implications. Some thinkers have argued that spreading to the stars is the only way to ensure humanity's long-term survival. Earth is vulnerable to various catastrophic risks: asteroid impacts, supervolcanic eruptions, pandemics, runaway climate change, nuclear war. A species confined to one planet is betting everything on that planet's continued habitability. A species spread across many worlds has backup copies, insurance against localized disasters. Historians still argue whether interstellar colonization would reduce existential risk or merely spread it around. Some point out that colonial populations often face new risks their home populations don't: unfamiliar diseases, environmental hazards, social upheavals. Others suggest that diversity and redundancy are always beneficial for long-term survival, regardless of the specific challenges each population faces. Then there's the question of contact with extraterrestrial intelligence. The universe has existed for nearly 14 billion years. If life arises readily, and many scientists believe it does, then intelligent civilizations have had plenty of time to develop elsewhere in the cosmos. The famous Fermi paradox asks why, if aliens exist, we haven't detected any sign of them. One possible answer: interstellar travel is impossible, trapping each civilization in its own stellar backyard. But if warp drives work, this answer collapses. Other civilizations might already be out there, crossing the galaxy, perhaps even monitoring young species like ourselves. First contact, the encounter between humanity and alien intelligence, might be not centuries away but decades or less. The implications for science, religion, culture and politics are almost beyond calculation. Consider what we might learn from a civilization millions of years older than ours. Their physics, their biology, their art, their philosophy, every domain of knowledge might be transformed by exposure to genuinely alien perspectives. Or consider the risks. Perhaps not all civilizations are friendly. Perhaps the reason the galaxy seems quiet is that the loud civilizations get noticed by predators. You feel a slight shiver despite your warm blankets, not entirely from fear, but from the sheer magnitude of what might be at stake. The development of warp drive wouldn't just be a technological achievement, it would be a civilizational transformation, a transition as significant as the development of agriculture, or writing, or industrialization. Humanity's story would enter a new chapter, one we can barely imagine from our current vantage point. Closer to home, warp technology would transform resource extraction. Asteroids in our own solar system contain vast wealth, metals, water, organic compounds, but they're difficult to reach with current technology. Other solar systems might contain resources even more abundant. Mining operations across multiple star systems could potentially end material scarcity entirely, providing unlimited raw materials for human industry. Energy acquisition would be transformed as well. Dyson spheres, hypothetical megastructures that capture a star's entire energy output, might become buildable if you can transport materials across interstellar distances easily. Civilizations capable of harnessing stellar energy would face no practical energy limitations for any conceivable project. Your eyelids have grown very heavy now, but your mind continues to wander through these possibilities. A humanity among the stars would face new challenges and new wonders. Old conflicts might persist or transform. New forms of cooperation and competition might emerge. The future is unwritten, but if warp drive works, it will be written across a much larger canvas than the single planet where our story began. There's something troubling that we should address before you drift off completely. Something that physicists have worried about ever since faster-than-light travel became theoretically conceivable. It involves causality, the principle that effects follow causes, and it might mean that even if warp drives work perfectly, they could create paradoxes that the universe itself might forbid. This is the kind of problem that keeps theoretical physicists awake at night, scribbling equations on napkins and wondering if they've missed something fundamental about how reality operates. The problem starts with a counterintuitive result from special relativity. When you combine faster-than-light travel with the relativity of simultaneity, the fact that different observers disagree about which events happen at the same time, you can construct scenarios where effect precedes cause. Information arrives before it's sent. Consequences happen before their antecedents. Messages from the future contaminate the past. This isn't science fiction speculation. It's a direct mathematical consequence of combining superluminal motion with Lorentz transformations. Here's a mainstream historical fact about when physicists first recognized this problem. The potential for causality violation in faster-than-light scenarios was discussed as early as the 1960s, decades before Alcubierre's warp drive paper. Einstein himself worried about related issues, though he never specifically addressed warp drives. The tachyon, a hypothetical particle that always travels faster than light, was analysed in detail, and physicists quickly realised that tachyonic communication would enable grandfather paradoxes. You could, in principle, send a message back in time telling your grandfather to never have children, thereby preventing your own existence and the sending of the message. Let's walk through how this works with warp drive specifically, because understanding the mechanism matters. Imagine you have two space stations, Alpha and Beta, separated by 10 light years. In your reference frame, the frame where both stations are at rest, they're synchronized. Clocks on both stations read the same time. Now imagine you activate a warp drive and travel from Alpha to Beta in 1 year of your subjective time, arriving effectively faster than light from the perspective of both stations. Here's where relativity creates trouble. Consider a third observer, Charlie, who's travelling at high speed relative to Alpha and Beta. Due to the relativity of simultaneity, Charlie's now is tilted relative to yours. Events that you consider simultaneous like clock readings on alpha and beta, Charlie considers sequential. When you arrive at beta, from Charlie's tilted perspective, you've actually arrived before you left. Your arrival is in Charlie's past relative to your departure. Now here's a quirky tidbit that makes this even stranger. The specific geometry of the tilt depends on Charlie's velocity. By choosing the right velocity, Charlie can make your arrival arbitrarily far in the past relative to your departure. And if you then use another warp drive to travel in a frame aligned with Charlie's perspective, you can return to alpha before you originally left. You've created a closed time-like curve, a path through space-time that loops back on itself. You can meet your past self, deliver warnings, change decisions, and create all the paradoxes that time travel stories love to explore. Historians still argue whether these paradoxes represent a genuine physical impossibility or merely a sign that our understanding is incomplete. Some physicists believe the universe has a chronology protection conjecture, a principle, not yet proven, that quantum effects or other mechanisms automatically prevent closed time-like curves from forming. Stephen Hawking proposed this conjecture and famously quipped that chronology protection keeps the universe safe for historians. But no one has proven that such protection exists or explained exactly how it would work. The paradoxes themselves are genuinely troubling. The grandfather paradox is the most famous. You travel back in time and prevent your own birth, which means you never exist to travel back, which means your birth isn't prevented, which means you do exist to travel back, and so on in an infinite logical loop. There's no consistent resolution. Either the universe forbids the scenario entirely, or something very strange happens. Multiple timelines, predetermined outcomes, or physics we don't understand. Some researchers have proposed that the universe might allow consistent time loops, but forbid inconsistent ones. In this view, if you travel back in time, you can only do things that were already part of the historical record. You can't change the past because the past already includes your future self's visit. This is called the Novikov self-consistency principle, and while it resolves the logical paradoxes, it raises troubling questions about free will and determinism. Are your actions in the past constrained by some cosmic force that prevents paradoxes? How would that constraint manifest physically? For warp drives specifically, the causality problem depends on the details of how the drive operates. The Alcubierre metric, in its standard formulation, definitely permits closed time-like curves under certain conditions. If you have two warp drives moving in different directions, or one warp drive observed from a moving reference frame, paradoxes become possible. This has led some physicists to argue that even if warp drives are energetically feasible, the universe might forbid them for causality reasons. The positive energy warp drives face similar concerns. The new proposals reduce or eliminate the exotic matter requirement, but they don't obviously solve the causality problem. Any mechanism that allows genuine faster-than-light travel, not just apparent superluminal motion like the expansion of space, runs into the same relativistic obstacles. The problem isn't the specific engineering of the warp bubble, it's the fundamental structure of space-time and how different reference frames relate to each other. You might wonder if there's any escape from this dilemma. Several possibilities have been proposed. Perhaps warp drives can only operate in a preferred reference frame, the cosmic rest frame defined by the cosmic microwave background, for instance. Travel would be faster than light in that frame, but wouldn't allow the multi-leg journeys that create paradoxes. This would require abandoning the principle of relativity, which says no reference frame is special, a significant modification to our understanding of physics. Alternatively, perhaps quantum mechanics resolves the paradoxes through mechanisms we don't yet understand. Quantum mechanics already permits phenomena that seem paradoxical from a classical perspective. Particles in two places at once, measurements that affect distant systems instantaneously. Perhaps a proper quantum theory of gravity would reveal that closed time-like curves are impossible, or that they're possible but don't lead to logical contradictions. Some physicists have even embraced the paradoxes, arguing that multiple timelines or many worlds interpretations might allow time travel without logical inconsistency. If travelling back in time creates a new branch of reality, rather than changing your original timeline, the grandfather paradox dissolves. You can kill your grandfather, but only in a newly created timeline. Your original timeline remains unchanged. Whether this interpretation makes physical sense or merely relocates the mystery remains hotly debated. You feel your thoughts becoming fuzzy around the edges, the sharp logical distinctions of causality blurring into the soft uncertainty of approaching sleep. The universe might be trying to tell us something important with these paradoxes. Perhaps faster-than-light travel is truly impossible, not because of energy requirements, but because it would break the logical structure of cause and effect. Or perhaps there's a resolution we haven't discovered yet, a way to have warp drives without time machines, interstellar travel without grandfather paradoxes. The honest answer is that nobody knows. The mathematics of general relativity permits warp drives. The mathematics of special relativity suggests they enable time travel. The mathematics of time travel generates logical contradictions. Somewhere in this chain, something must give. Either warp drives are impossible for reasons we don't fully understand, or time travel is possible but somehow non-paradoxical, or our mathematical frameworks are missing something crucial about how reality actually works. For tonight, you let the paradoxes remain unresolved, floating in the darkness of your bedroom like Schrödinger's cat, simultaneously possible and impossible until someone finally opens the box. The scientific community's reaction to warp drive research tells you something important about how frontier physics actually works. You might imagine that bold new ideas get immediate attention and rigorous testing, but the reality is messier, more political, and considerably more human. Physicists are people too, with reputations to protect, limited time and resources, and reasonable skepticism about claims that sound too good to be true. When Alcubierre published his warp drive paper in 1994, the reaction was mixed. Some physicists found it fascinating, a clever demonstration that general relativity permitted surprising solutions. Others dismissed it as a mathematical curiosity with no physical relevance, pointing to the exotic matter requirements as proof that the whole thing was essentially science fiction, dressed up in equations. The mainstream consensus settled into cautious acknowledgement. Interesting idea, almost certainly impossible to build, probably not worth serious research investment. Here's a mainstream historical fact about how academic incentives shape what gets studied. Physics research depends heavily on grants from funding agencies, which tend to favour projects with clear near-term applications or strong theoretical motivation from established frameworks. Warp drive research fits neither category well. It's too speculative for applied physics funding and too engineering-focused for pure theoretical physics funding. Researchers who dedicated significant effort to warp drives often did so at some cost to their mainstream careers. This created a selection effect. The physicists who worked on warp drives tended to be either very senior, with established reputations that could absorb some unconventional work, or very independent, working outside traditional academic structures. Harold White at NASA pursued warp research as a small side project within a larger portfolio of advanced propulsion concepts. The Applied Physics Group operates independently precisely to escape the constraints of traditional academic funding. Maverick researchers in various countries contributed occasional papers without making warp drives their primary focus. Now here's a quirky tidbit about the sociology of fringe physics. The warp drive community exists in a delicate space between legitimate theoretical physics and the crankosphere of perpetual motion machines and free energy devices. Conferences on advanced propulsion sometimes attract both serious researchers and enthusiasts whose understanding doesn't quite match their enthusiasm. Navigating this social terrain requires skill. Maintaining scientific rigor while remaining open to unconventional ideas, engaging with criticism constructively while not letting skeptics shut down inquiry prematurely. Historians still argue whether mainstream physics has been appropriately cautious or excessively dismissive of warp drive research. Some point to the history of other fringe-seeming ideas that eventually became mainstream: continental drift, the bacterial cause of ulcers, the expanding universe, and suggest that more resources should have been devoted to testing warp concepts. Others argue that with limited research funding, prioritizing well-established physics over speculative propulsion systems is entirely reasonable. The positive energy warp drive proposals have shifted this dynamic somewhat. By eliminating or reducing the exotic matter requirement, they address the objection that warp drives require physics that might not exist. The remaining objections are about scale and engineering rather than fundamental possibility. This makes the research more respectable in mainstream eyes, though substantial skepticism remains. Peer review of warp drive papers tends to be particularly rigorous. Reviewers know that any errors will be seized upon by skeptics, and that the media will sensationalize any positive results. Authors must be careful to state limitations clearly, avoid overclaiming, and demonstrate mastery of the relevant physics. This scrutiny is healthy. It maintains quality and prevents the field from drifting into pseudoscience, but it also raises the bar for publication and slows the pace of progress. Some physicists object to warp drive research on philosophical grounds. They argue that resources spent on speculative propulsion should instead go to more promising areas: quantum computing, materials science, renewable energy. The opportunity cost of warp research in this view is progress on problems we might actually solve within our lifetimes. This argument has force, but it also assumes we can reliably predict which research directions will prove fruitful, an assumption that history repeatedly challenges. The media plays a complicated role in all this. When warp drive papers get published, they often generate headlines that oversimplify or sensationalize the results. NASA working on warp drive sounds much more exciting than NASA researcher explores theoretical framework that might someday inform advanced propulsion concepts. The gap between headline and reality frustrates scientists, who then become more reluctant to engage with media at all. This creates a feedback loop where public understanding of frontier physics grows increasingly distorted. You think about the researchers scattered across universities and laboratories, pursuing these ideas despite limited funding and occasional ridicule. They're not stupid or naive. They understand the challenges, the skepticism, the low probability of success. They pursue warp research anyway because the question fascinates them, because the payoff if it works would be civilization changing, because someone needs to explore the boundaries of what physics permits. This is how science often advances at the frontier, through stubborn individuals who refuse to let interesting questions die, even when the mainstream has moved on. Most frontier research leads nowhere, but occasionally a stubborn researcher pursuing an unfashionable idea makes a breakthrough that changes everything. We can't know in advance which stubborn researchers are wasting their time and which are planting seeds for future revolutions. The current state of warp drive research might best be described as respectable speculation. The theoretical foundations have been explored in peer-reviewed papers. The mathematical frameworks are sound. The engineering challenges are understood, at least in broad outline. What's missing is any experimental evidence that warp effects can be created, even at microscopic scales. Until such evidence appears, warp drives remain firmly in the theoretical realm. Some researchers are working on exactly this problem. designing experiments that might detect tiny space-time distortions under laboratory conditions. The challenges are immense. The effects predicted are smaller than current measurement technology can detect. New approaches, new instruments, new techniques are needed. Progress is slow, but it continues. You feel a kind of admiration for these patient researchers as you drift towards sleep. They're playing a very long game, knowing they might never see results in their lifetimes. They're maintaining a flame of inquiry that future generations might use to light their way to the stars. That's a kind of faith, not religious faith, but scientific faith that careful thinking and persistent effort eventually leads somewhere worth going. The universe keeps its secrets well, but it has never yet managed to hide them forever from determined human curiosity. In the quiet corridors of NASA's Johnson Space Center, far from the glamorous launches and triumphant mission controls that capture public imagination, small teams have occasionally pursued ideas that sound like they belong in science fiction. You picture fluorescent-lit offices, whiteboards covered in equations, researchers who spend most of their time on conventional propulsion, but carve out hours for something stranger. This is how NASA has quietly kept the warp drive dream alive, even as official priorities focused on more immediately practical goals. Harold White became the public face of NASA's warp research in the 2000s. Working within the Advanced Propulsion Physics Laboratory, nicknamed EagleWorks, he and his colleagues explored both the theoretical frameworks and potential experimental approaches for detecting warp-like phenomena. The budget was tiny by NASA standards, the work was speculative, and expectations were appropriately modest. But the research happened, and it generated both genuine scientific output and considerable public interest. Here's a mainstream historical fact about how NASA has historically balanced practical missions with far future concepts. The agency has always maintained small programs exploring revolutionary propulsion ideas, from nuclear thermal rockets in the 1960s to ion drives that now power actual spacecraft. Most of these programs produced nothing immediately useful, but some yielded technologies that later proved valuable. The willingness to invest small amounts in speculative research has been a consistent feature of NASA's approach, even during budget-constrained periods. White's work focused on two main areas. Theoretically, he explored modifications to the Alcubierre metric that might reduce energy requirements, the oscillating warp field concept mentioned earlier. Experimentally, he built the White-Jude warp field interferometer, designed to detect extraordinarily subtle space-time distortions that might indicate the experimental setup was generating something warp-like. The interferometer never produced confirmed positive results, but the attempt itself demonstrated that experimental approaches to warp physics weren't entirely out of reach. Now here's a quirky tidbit about the reaction to White's work. When news of NASA's warp research reached the public, the response was overwhelming. People desperately wanted faster-than-light travel to be possible, and the fact that NASA was investigating it seemed to validate their hopes. Scientists had to repeatedly clarify that the research was highly preliminary, that no warp fields had been created, that practical warp drives remained far beyond current technology. The gap between public excitement and scientific caution reflected a deep human yearning for the stars that no amount of technical caveats could dampen. Historians still argue whether NASA's warp research represented a wise investment of limited resources or a distraction from more pressing goals. Critics pointed to the lack of concrete results and suggested the agency was chasing headlines rather than science. Supporters argued that maintaining some investment in revolutionary concepts was essential for long-term progress, that betting everything on incremental improvements would never lead to transformative breakthroughs. Other space agencies have shown varying degrees of interest in advanced propulsion concepts. The European Space Agency has funded occasional studies of breakthrough physics for space travel. The Chinese space program has reportedly explored similar ideas, though details are scarce. Private companies like SpaceX have focused almost entirely on conventional chemical rockets, optimizing existing technology rather than pursuing revolutionary alternatives. The result is a fragmented landscape where warp research happens in scattered pockets without coordinated effort. The DARPA approach offers an interesting contrast. The Defense Advanced Research Projects Agency funds high-risk, high-reward research that conventional funding sources won't touch. They've supported work on everything from stealth aircraft to the internet, often pursuing ideas that seemed crazy until they worked. Some have suggested that warp drive research belongs in a DARPA-style portfolio, unlikely to succeed, but transformative if it does. Whether military applications of warp technology would be desirable is another question entirely. You think about the institutional challenges of pursuing long-term speculative research. Space agencies face constant pressure to demonstrate near-term results, successful launches, new discoveries, missions that capture public imagination. Warp research offers none of these in the short term. It requires patience measured in decades or centuries, continued investment despite repeated null results, faith that the theoretical framework is sound even without experimental confirmation. This is why independent organizations like Applied Physics have become increasingly important in warp research. Operating outside government funding constraints, they can pursue long-term agendas without justifying each year's progress to congressional committees. They can attract donors who care about humanity's long-term future, rather than the next election cycle. They can build institutional knowledge across decades, rather than losing it to career changes and budget cuts. The applied physics approach also enables interdisciplinary collaboration that traditional academic structures make difficult. Warp drives sit at the intersection of general relativity, quantum field theory, materials science and engineering, fields that rarely talk to each other in conventional universities. Creating a dedicated organization focused on a specific goal allows expertise from multiple domains to be brought together in ways that departmental boundaries normally prevent. Some futurists have proposed even more ambitious institutional structures for warp research. A true interstellar development program might require resources comparable to the Manhattan Project or the Apollo program, tens of billions of dollars, thousands of researchers, decades of sustained effort. Whether any government or private entity would commit such resources to a goal with such uncertain prospects remains doubtful. But the possibility exists, waiting for some future generation that decides the stars are worth the investment. You imagine a future research centre, perhaps built in the quiet of space itself, where engineers and physicists work on problems that will take centuries to solve. They're not racing against competitors or struggling for annual funding. They're building something for descendants they'll never meet, driven by the same impulse that led ancient peoples to plant olive groves they would never see bear fruit. The stars are patient. Perhaps humanity can learn to be patient too. You're deep in the territory between waking and sleep now, and your thoughts turn to timelines, not the timelines of physicists' paradoxes, but the timelines of human development. When might your descendants actually board a warp-capable starship? What intermediate steps might bridge the gap between today's theoretical papers and tomorrow's interstellar voyages? The answer involves speculation, but it's speculation grounded in the patterns of how transformative technologies have developed before. Start with the near term, the next few decades. During this period, warp research will likely remain primarily theoretical. The positive energy warp drive proposals need to be refined, extended, tested against objections, and integrated with quantum field theory. Experimental approaches will be designed and attempted, though significant positive results seem unlikely soon. The groundwork is being laid, the questions are being sharpened, but the answers remain elusive. Here's a mainstream historical fact about technology development timelines. The gap between theoretical breakthrough and practical implementation varies enormously depending on the technology. Sometimes it's quick. Just 12 years separated Einstein's explanation of the photoelectric effect from the first working photocell. Sometimes it's slow. Nearly a century passed between Maxwell's equations predicting radio waves and the development of practical radio communication. Predicting where warp drives fall on this spectrum is essentially impossible at our current level of understanding. During this near-term period, other propulsion technologies will advance. Solar sails are already being tested in space, and improvements could enable faster travel within the solar system. Nuclear thermal propulsion might finally move from concept to reality, providing more efficient engines for Mars missions and beyond. Laser-pushed light sails, the concept behind the Breakthrough Starshot initiative, might accelerate tiny probes to significant fractions of light speed, reaching nearby stars within decades rather than millennia. These intermediate technologies matter for warp development in indirect ways. They expand humanity's presence in space, building the infrastructure and expertise that more advanced propulsion would eventually require. A civilization that has established permanent presence on the Moon, Mars, and the asteroid belt is better positioned to attempt interstellar travel than one still confined to a single planet. Each step outward builds capacity for the next step. Now here's a quirky tidbit about the psychology of technological forecasting. Humans consistently overestimate what will happen in 10 years and underestimate what will happen in 50. We imagine near-term futures that look too much like the present with minor additions, and distant futures that look too much like science fiction without the incremental steps that connect here to there. Warp drive development probably won't follow either pattern, neither impossibly soon nor safely distant, but threading some unpredictable path through discoveries we can't currently anticipate. Historians still argue whether technological development follows predictable patterns or is fundamentally chaotic, driven by individual geniuses and lucky accidents that can't be foreseen. The optimistic view suggests that sustained investment in fundamental research reliably produces breakthroughs. The pessimistic view notes that many heavily funded research programs have produced disappointing results, while transformative discoveries emerge from unexpected quarters. Warp drives might eventually benefit from either pattern, or might remain forever theoretical despite humanity's best efforts. Looking further ahead, perhaps a century or two, the picture becomes hazier, but also more hopeful. If energy production continues advancing along historical trends, the power requirements for warp drives might become achievable. Fusion power, if perfected and scaled, could provide enormous energy densities. Space-based solar power, collecting sunlight without atmospheric interference, could eventually approach the scales needed. Exotic energy sources we haven't discovered yet might prove even more capable. Material science will likely advance dramatically over the next century. New metamaterials with properties not found in nature might enable precise shaping of electromagnetic and gravitational fields. Quantum materials operating at room temperature might permit manipulation of vacuum energy. Advances in nanotechnology might enable construction at scales and precisions currently impossible. Each of these developments, while not directly related to warp drives, could contribute to the eventual solution. The development of artificial general intelligence, machines that can think as flexibly as humans, might accelerate progress in ways that are difficult to predict. An AI physicist, capable of processing vast quantities of data and exploring theoretical possibilities far faster than human researchers, might find solutions that would take humans centuries to discover. Alternatively, AI might prove less creative than hoped, accelerating routine research without making the conceptual leaps that breakthrough physics requires. Your descendants 5 or 10 generations hence might look back on our era as the primitive beginning of the interstellar age, the time when the first theoretical foundations were laid. Or they might look back and shake their heads at our naive optimism, still confined to our solar system despite centuries of effort. We genuinely cannot know which future awaits. What we can do is make choices that keep both possibilities open. Investing in fundamental physics research maintains the option of discovering warp-enabling breakthroughs. Expanding into the solar system builds infrastructure and expertise. Developing sustainable civilizations ensures that future generations exist to pursue these goals. Even if warp drives prove impossible, these investments have value. If warp drives prove possible, they're essential prerequisites. You think about your great-great-grandchildren, whoever they might be, whatever world they might inhabit. Perhaps they'll be born on Mars, or in orbital habitats, or on worlds orbiting other stars. Perhaps they'll look at the night sky and see not distant points of light but familiar destinations, places their friends have visited and sent messages from. Or perhaps they'll look up at the same unreachable stars their ancestors did, still dreaming of journeys that remain forever beyond reach. Either way, they'll inherit the curiosity that defines humanity, the need to know what lies beyond the horizon, the refusal to accept impossible as a final verdict. That curiosity has carried us from African savannas to the moon. It might yet carry us to the stars. The timeline remains uncertain. The destination remains compelling. The journey for now continues through dreams. The night has grown very deep now, and your thoughts have slowed to match the gentle rhythm of your breathing. The equations and paradoxes and engineering challenges have faded into a soft background hum, leaving something simpler and more profound: the human desire to reach outward, to explore, to know what lies beyond. You've been on quite a journey tonight, traversing the landscape of theoretical physics without ever leaving your comfortable bed, exploring possibilities that might transform civilization or might remain forever out of reach. You've travelled far tonight, from Einstein's patent office to NASA's quiet laboratories, from rubber sheet analogies to quantum vacuum fluctuations. You've contemplated distances that dwarf anything in ordinary experience and timelines that stretch across generations. You've faced the possibility that faster-than-light travel might be forever impossible, and the possibility that your descendants might actually achieve it. Both possibilities remain open, like unopened doors in a vast mansion of the universe, waiting for future explorers to test their locks. Here's a mainstream historical fact to carry with you into sleep. Every generation has faced the unknown and wondered what might be possible. The ancient Greeks looked at the moon and imagined it as a world they could never visit, crafting myths about gods and chariots to explain its movements across the sky. The medieval Europeans looked at the Western Ocean and imagined lands beyond the horizon that might or might not exist, terrifying and enticing in equal measure. The 19th century dreamers looked at the sky and imagined flying machines that seemed impossible in their time, sketching contraptions with wings and propellers that their contemporaries dismissed as fantasy. Each generation pushed a little further, expanded the boundaries of the known, converted impossibilities into achievements. The pattern suggests something fundamental about human nature: an inability to accept limits as permanent, a compulsion to test every boundary and probe every barrier. Whether this makes us wise or foolish depends on whom you ask. What's undeniable is that it makes us human. Now here's a quirky tidbit for your drowsy contemplation. Some researchers who work on warp drives report that the work itself brings them joy, regardless of whether practical implementation ever occurs. There's something deeply satisfying about exploring the boundaries of what physics permits, about pushing equations to their limits and discovering unexpected possibilities. The journey matters even if the destination remains unreached. The questions matter even if the answers stay hidden. One physicist described warp research as recreational mathematics with cosmic implications, a hobby that happens to concern the fate of interstellar civilization. Historians still argue whether humanity's reach exceeding its grasp is tragic or heroic, whether we should dream within our means or always strive for what might be impossible. The debate has continued since the first Greek philosophers and shows no signs of resolution. Perhaps both perspectives contain truth. Perhaps wisdom lies in dreaming boldly while working patiently, in hoping for breakthroughs while preparing for slow progress. The stars will wait for us regardless of which approach we take. They've been waiting for billions of years already. The researchers working on positive energy warp drives today are planting seeds in soil whose fertility remains unknown. They might be nurturing trees that will bear fruit in centuries. They might be tending gardens that will never bloom. Either way, the act of planting reflects something beautiful about human nature. Our willingness to invest in futures we won't personally see. Our ability to find meaning in efforts whose results remain uncertain. There's a kind of faith in this, though it's not religious faith. It's faith in the value of inquiry itself, in the pursuit of knowledge for its own sake as much as for any practical application. You feel your body sinking deeper into the mattress, your muscles releasing tension you didn't know you were holding. The stars outside your window have shifted slightly as the Earth continues its ancient rotation, carrying you around a sun that carries you around a galaxy that drifts through an expanding universe. You're already travelling through space at incredible speeds, surfing gravitational waves and cosmic expansion, a passenger on a planet-sized starship that has carried life for billions of years. Warp drive or no warp drive, you're a cosmic voyager simply by existing. Perhaps that's enough for one night. Perhaps the warp drives and interstellar voyages can wait for another evening, another exploration, another journey through the soft territories between waking and sleeping. Tonight, you've wandered far enough. Tonight, the comfortable darkness of your bedroom is voyage enough. The blankets around you form their own kind of protective bubble, shielding you from the cold vastness beyond while you rest and dream. The universe is vast beyond comprehension, old beyond imagining, strange beyond expectation. It contains wonders we've discovered and wonders that remain hidden. It permits phenomena we once thought impossible and forbids others we desperately wish were allowed. Its rules are written in mathematics we're still learning to read, in physics we're still struggling to understand, but we're learning. Slowly, imperfectly, we're learning. And somewhere in that vast and ancient and strange universe, there might be a loophole, a way to bend space rather than traverse it, a shortcut through the cosmic distance that separates us from the stars we dream about. The mathematics suggests it might exist. The engineering challenges are immense but perhaps not insurmountable. The paradoxes are troubling but perhaps resolvable. The researchers continue their quiet work, generation after generation, passing the torch of inquiry from one set of curious minds to the next. Tonight, as you drift towards sleep, let that possibility float gently through your consciousness. Not as a certainty. Certainty is too heavy for dreams. Not as a fantasy. Fantasy is too light for science. But as a hope, a question, a door that might open someday. The positive energy warp drives that researchers proposed so recently might lead somewhere revolutionary, or might prove to be another beautiful dead end. We won't know for decades or centuries, but the question itself enriches our understanding of the universe, and the pursuit itself reflects the best of what humanity can be. Your breathing has become very slow now, barely perceptible, like the faint pulse of starlight crossing the void between galaxies. The journey through tonight's topic has reached its gentle end. The equations have dissolved into the darkness like morning mist evaporating in gentle warmth. The challenges have faded into the background, no longer demanding attention, simply resting alongside you in the quiet darkness of the room. What remains is the simple, profound truth that humans look up at the stars and wonder. They have always wondered, since the first of our ancestors tilted their heads back and saw those points of light scattered across the darkness. They will always wonder, as long as there are minds capable of curiosity and hearts capable of longing. And perhaps someday, wondering will become going, dreaming will become travelling. The impossible will become routine as the airplanes that would have seemed miraculous to your great-grandparents. But for now, sleep. Let the stars keep their vigil outside your window, patient sentinels of an ancient universe that has watched countless worlds form and dissolve. Let the physicists continue their patient work in laboratories you'll never visit, scribbling equations that might someday change everything. Let the future unfold in its own time, at its own pace, carrying humanity toward whatever destiny awaits among the infinite possibilities that quantum mechanics and general relativity permit. The night holds you gently, like space holds the stars, not grasping, not constraining, just cradling in a vast embrace that asks nothing and offers everything. The silence deepens, soft and warm as the cosmic microwave background that fills the universe with its ancient whisper. Your thoughts grow quieter still, slowing to the rhythm of the rotating Earth, the orbiting moon, the wheeling galaxy. And somewhere in the vast darkness of the cosmos, light continues its ancient journey between the stars, patient, constant, waiting for the day when something faster might finally join it in that endless dance across the void. Perhaps that day will come, perhaps it won't. Either way, the universe will continue being beautiful, mysterious, and worthy of our attention. Rest now, traveller. Dream of distant suns and warped space-time and the endless frontier that awaits beyond the horizon. The universe will still be there when you wake, full of mysteries and possibilities and the endless invitation to explore. Sweet dreams, the stars will wait,